Okay, so in the circuit, let's say we have this RL circuit, right? Let's say there's an initial, there's a voltage source of 120 volts and an initial current of 6 milliamps. And let's say we have a 10k ohm and a 20 millihenries inductor in the circuit. We need to try to find the current I sub t, which is I after 1 microsecond, using 1 microsecond for the, after 1 microsecond of closing the switch. I want to find out what is that current gonna be. Alright, so let's get into it. Based on the equation that governs that, we know that the current at any time is equal to I sub naught e to the minus t over L over R, right, which is tau, plus V battery divided by R, right, bracket 1 minus e to the minus t over L over R, which is tau again. So we can substitute in here to find actually what the current is going to be after 1 microsecond. So I 1 microsecond is equal to I naught, which is 6 milliamp, which is 6 times 10 to the minus what? 10 to the minus 3 e to the minus t 1 times 10 to the minus 6 divided by L. What's L? L is 20 times 10 to the minus 3 henries, again divided by R, which is 10k, which is 10 times 10 to the third. Let's work this piece out first. Plus V battery, what is the V battery, is 120 volts divided by R, which is 10k, which is 10 times 10 to the third ohms, right, times 1 minus, this is 1, minus e to the minus t, e to the minus 1 times 10 to the minus 6 is t divided by tau, which is L over R, again L is 20 times 10 to the minus 3 divided by R, which is 10 times 10 to the third. Now, you gotta work all this out to determine what's gonna be for that, for I. So let's break it down further here. I at 1 microseconds, my apologies, 1 microseconds. If you multiply this piece out, which is our numbers that might give us some problems here, we're going to be careful. L over R, which is 20. This is 20 times 10 to the minus 3, or 0.123, 0.002. Right, that's 20 times 10 to the minus 3 divided by what's that, 10,000? 10,000. Okay. Okay. So that's basically e to the minus 1 times 10 to the minus 6 divided by 2 times 10 to the minus 7. Right, so this piece comes out to 2 times 10 to the minus 7. So we could substitute that piece there. So what is E minus 1 times 10 to the minus 6 divided by 2 times 10 to the minus 7? So this is gonna comes out to, based basically that cancels, that comes to 1, 10 to the minus 1. So that's going to be 1, 10 to the minus 1 over 2, 10 to the minus 1. 10 to the minus 1 is 0.1, so 0.1 divided by 2 basically. Right, so this 0.1 divided by 2 is 0.05. 2.05. So all this gonna becomes e to the minus 0.05. Again, this is gonna be 1 minus e to the minus 0.05 here, right? Multiply by 6 times 10 to the minus 3. Right. So let's see what E let's see what E times 0.05 equals to. That's 1.05, right? So now it's going to be 1.05 multiplied by 6 times 10 to the minus 3, right? So that becomes, this piece becomes 6.3 times 10 to the minus 3. So right up here, it becomes 6.3 times 10 to the minus 3 plus this piece 120. So again, e to the minus 0.05, e to the minus 0.05. Hold on, I did something wrong here, didn't I? This might be wrong. Give me a second here. Let me do a correction. E to the minus 0.05, e to the minus 0.05 equal is actually 9.5. My apologies again on this one. So these numbers would be wrong. So this would come out to 9.5 times 10 to the minus 1, right, times 6.3. This one would be plus, then this would be 120 divided by 10,000 is equal to 1.2 times 10 to the minus 2, right? And again, this would have now been 1 minus 9.5 times 10 to the minus 1. This is actually 0.95 actually, right, if you look into it. So this is actually 0.95, the same thing as 0.95. Plus that. Alright. So all that piece there would come out to that. So 6.3 times 0.95. 6.3 times 10 to the minus 3 times 0.95. So 6 times 0.95 is equal to 5.7. So this becomes 5.7 from here. We go up top. 5.7 5.7 times 10 to the minus 3 plus this piece, 0.05 times 1, 2, 3.0012 plus this piece becomes why is that number so small? It is what it is. It becomes 6.10 times 10 to the minus 5. Well, if you add those two plus 0.0057 1, 2, 3. This becomes equal to 5.76 times 10 to the minus 3. That will be the current I after 1 microseconds. Right, so this is equal to 5.76 milliamps. Interesting, because what that means is that the current flow is actually changing. It decreases from the initial current state. It will decrease from 6 milliamps to 5.7 milliamps, and that would be the current after that 1 microsecond. Now, what about the voltage relationships? How do we find this voltage relationship? Well, voltage across the resistor at that time of 1 microsecond will be I of t times R. I of t is then 5.76 milliamps, or 5.76 times 10 to the minus 3 amps times the resistance of 10k, 10 times 10 to the third. Right, so that voltage V sub R after that time becomes 57.6 volts. So after 1 microsecond, 57.6 volts will be across the resistor. Right? Well, that voltage will be across the resistor. What about across the inductor? Well, since the total voltage, right, V battery equals VR plus VC, then V battery is 120 volts. That means V sub C at that time will be equal to V battery minus VR. So V battery is 120 volts minus VR at that time of 1 microsecond will be 57.6 volts. So when you subtract that, 120 volts minus 57.6 equal 62.4. It's going to be 62.4 volts will be the voltage across the capacitor at 1 microsecond, after 1 microsecond. With an initial current obviously of 6 milliamps, right? That's cool. That's cool calculation for you. So that's the voltage across the the voltage across the inductor. What am I talking about? Capacitor. Voltage across the inductor. Right. So V sub L is equal to 62.45. My error there. So 62.45 volts to 62.4 volts will be across the inductor after 1 microsecond, giving an initial current of 6 milliamps. right? Now, so VL and we have VSR. Now, suppose let's look at the circumstances now when I sub naught is equal to that same 6 milliamps, and we have a discharging situation, right? What will happen if we should, for instance, let's say that initial, actually let's start it like that. Let's say that initial I sub naught is the maximum current flow, right? And what is the maximum possible current flow? Probably when this is acting as a short circuit, the inductor acting as a short circuit. So what's going to happen when that inductor acts as a short circuit is that V, let's say it started at V over R, right? Which means that this acts as a short circuit. So let's say the maximum I sub naught then is equal to V over R, which is the voltage of 120 volts divided by R of 10 times 10 to the third, which is the 10k ohm resistor, right? So that works out to be 12 milliamps. So let's assume I sub naught is 12 milliamps, and let's work out for IT after what's gonna happen after 500 milliseconds. Maybe that's too much. Let's say after for discharging 10 milliseconds, right? 10 milliseconds. Let's see what happens after 10 milliseconds. Okay, let's pause it for a while and get rid of this and work it out in a discharge situation. Okay, so welcome back. So we got rid of the charging situation. Now we look at the discharging situation, but this time I want to see, okay, what happens 10 milliseconds into the discharge. If there's a current worked out here, say maximum current for initially in the inductor of 12 milliamps, we're gonna assume maximum current flow, right? Let's assume initially there's a maximum current flow of 12 milliamps. And what's gonna happen here in this circuit? What's gonna happen to after 12 milliamps, 12 milliseconds, after 10 milliseconds, what's going to happen with IT? What's going to happen with VT, VR, and VC, VL, V sub L, after those times, okay? Let's start with the current. In a discharging situation, obviously if it's discharging, this is 0 volts for source, so 0 volts is V sub R after T plus V sub L after sometimes T, right? In a discharging situation, I of T is equal to I sub naught e to the minus TL over R for this inductor and this resistance series. So right away we could figure out what the current is going to be during 10 milliseconds into this discharge. Right, it's going to be I sub naught is actually 10 milliseconds. That's this 12 times 10 to the minus 3 amps there, times e to the minus t. What's t? T is actually 10 times 10 to the minus 3, which is 10 milliseconds, divided by L. What is L? L is inductor, which is 20 times 10 to the third, 10 to the minus 3, my apologies there, 10 to the minus 3 henries, and divided by L over, what is R over L, right? Just hold on, let me see, R, tau equal R over L, right? tau equal L over R. Tau equal L over R. So L is 20 divided by R. Right? Shoot. Did I make that mistake? I hope I didn't. Tau equal L over R though, right? Tau equal L over R. Alright, so tau equal L over R. So what is L? 20 times 10 to the minus 3 over R, which is 10,000. 10 times 10 to the third is equal to, so if you divide this out, if you multiply this out, what you're gonna get is let me see, multiply e to the minus 10 over R, let's divide it by that. So that is 10 to the minus 6, 2 times 10 to the minus 6. So break it down a little bit more. This becomes e times 2 times that divided by that is 10 to the minus 6 over 10 to the minus 3. Okay. 10 to the minus 6 divided by 10 to the minus 3. Interesting. Okay. That becomes a big number. That becomes 10 to the third and 10 to 5, right? I don't know if this is penable. That might be stretching it. So obviously this is a minus, right? This is a minus. Let's see what's going on with that. This is a minus here. 12 times 10 to the minus 3. Okay. Alright, so shift E times let's see. That didn't make no sense, does it? Wow. So what that is saying is that because let's look at those numbers again. T L is 20 times 10 to the minus 3. 20. That is just 0.0. 0.02 divided by 10,000. Two times 10 to the minus 7. Yeah, that's 2 times 10. That's how this is minus 7. 2 times 10 to the minus 7. As I worked that out before. And then this number becomes minus 7. This becomes 4, right? This makes it even bigger. But that big number right there gonna work out to 0, which makes the current flow 0. So 10, that's 5, minus 5 times 10 to the e to the minus is 0. So 0 times that becomes 0. So the current flow, what it is saying is that the current flow after 10 milliseconds in such a circuit is equal to 0. And this number is going to go 10 to 0. Such a big number, right? It's going to 10 to 0. So where they made the no current flow? Huh? No current flow. After 10 milliseconds, that don't make sense. Does it make sense? Initial current T over tau, if this number is tending to 0, that don't make no sense then. Right? There's going to be a voltage across what? Take time and record it properly. This is 10 milliseconds. L over R. This is going to be L over R. L is... yes, L is correct. Because L is 20 millihenries. So, that's going to make that 10 to the minus 7. 10, 10. Deal with this piece first. 20 over that. What makes that? This is 2 times 10 to the minus 6. I'm getting too much errors here. This is minus 6. This would have been minus 3. Minus 3 into 3. Yeah. So this is tending to 0. The current flow is tending to 0. Are you going to say if the current flow is tending towards 0 during this discharge situation? That means the voltage, obviously, which is V sub R of T, will be also equal to 0 since V sub T equal I naught R e to the minus T over tau L over R. It's gonna be 0, so V sub R is 0 and V sub L is after 10 milliseconds we're talking about. It's gonna also be equal to 0. So what this is saying is that because V sub L, V sub L is also negative I sub naught R e to the minus T over L over R. So, and that goes to 0 too, because this piece is going to go to 0 in both situations there, right? So remember again, this is a discharge situation. Don't mistake, think it's a charge situation. So what this is saying is that after 10 milliseconds, the system will already discharge through the resistor. It would have already taken away all the power, would have already burnt out through the resistor. So that's why the voltage across the resistor and the voltage across the inductor at that point would have been 0, because this is a discharging situation, right? So that actually makes sense. It took us a little while to kind of see that, but you have to realize this is a discharging circuit, and once you close that switch, then basically what you're doing is the discharge in the inductor, whatever power, how should I say, whatever was across the inductor in terms of supplying through the resistor will already discharge through the resistor, and the voltage that across the resistor and the inductor at that point would have been 0. What about if it's a very, very small time, right? Let's say it was like 1 microsecond like we had in the previous for the charging. How would the circumstances differ here? Well, let's see what happened. At that point, if it was 1 microsecond though, right? And in initial current was 12 milliamps, right? We had said that was 12 times 10 to the minus 3. Right, then, right, doing that e to the minus t over tau, t would have been 1 times 10 to the minus 6, right? And then if you work out L over R, let's do L over R separate, so it don't get confusing. L, which is 20 times 10 to the minus 3 over R, which is 10 times 10 to the third. That would have been 2 times 10 to the minus 6. No, this is now 2 times 10 to the minus 6. Now this would have been different now, right? Because these numbers would have been closer to numbers that make sense when using factorial. So that would have been e to the minus a half now, right? So this would have been shift e to the minus 0.5 equal. Now we start getting some numbers that make sense, that make more sense for these things. So this would have been 0.606. So this would have been 12 times 10 to the, is this 12 minus 3? Yeah. 12 times 10 to the minus 3 multiplied by 6. Let's just put a number here. 0.606. Right? This would work out to, alright, so 12 times 10 to the minus 3 is 0.012 times 0.606 equal, okay, now what you have is 7.27 times 10 to the minus 3 amps. See? So now you have 7.27 milliamps would have been the discharging current. Remember our initial current is 12 milliamps. Now it's gone down to 7.27 after 1 microsecond. Now we could work for the voltage at this point though, right? Now let's find VR after 1 microsecond, which is the voltage across the resistor in this discharging situation. Remember we're doing the discharging situation for the RL, right? So let's find this voltage across the resistor after 1 microsecond. And according to the discharging equation, V sub R is going to be I sub naught R e to the minus t over tau, which is L over R, right? This is L over R. That's the equation we're using. So I sub naught is 12 times 10 to the minus 3. And R here, what's R? Resistor is 10K, right? 10 times 10 to the third, right? Now we have e to the minus, all this can be worked out. Remember we worked this out, we know that e to the minus t over 2 over L over R is actually 0 point, which piece? L over R is 2.26, so 0.6, right? E to the minus 10, all this comes to 0.606, right? That's what we worked out for that piece, 0.606. So we could just substitute that 0.606 right here, correct? So now you have VR is equal to 12 times 10, which is 120. So 12 times 10 0.606, right? That's 7.2 times 10. So that's equal to 72.7 volts, right? That is V sub C, sorry, V sub L at 1 microsecond. It's going to be what? 120 volts minus 72.7 volts. I'm going to prove it both ways. So let's say this is 120 minus 72.7, right? That should come out to 47.3 volts. Let's see if it pans out the other way, because the equation the other way is V at 1 microsecond is equal to minus I sub naught R times e to the minus t over L over R, right? Now minus I sub naught 12 times 10 to the minus 3, right, times R. What is R? R is 12. R is what? R? Well, 10k. 10 times 10 to the third. Is this VR and VL the same thing? What is VL? VR. Interesting. So it's not actually, it's not this. It's negative of that. That's wrong. VL is minus VR based on the discharging situation. So it's going to pan out to be the same thing, except it's going to be negative. So it's going to be negative 72.7. Right, so remember that sum of the two in the discharging situation, the voltage source, there's no voltage source no more. So everything has been a balance between the inductor and the resistor voltages. In this case, the voltage will be leaving the inductor into the resistor and continuously discharging there. So whenever the inductor loses, the resistor will gain in that circumstances until the system totally discharges. So there ends our answer for both V sub L and V sub R. This is V sub R. This is V sub L. Discharging through the resistor, and after a time this value will tend to go down after a longer time. So maybe after 2 milliseconds you could assess and see how the value is decreasing.